Hi everyone, I would like to welcome you to the second lecture on the course on absorbed dose measurement for high energy photon and electron beams. In this lecture, we will discuss the code of practice TRS 398 protocol for absorbed dose determination for cobalt-60 unit and absorbed dose determination for high energy X-ray beams. What are the things needed when you start measurement? One is the water phantom. And the second one is the calibrated ionization chamber with the calibration factor traceable to PSDL. You can also use parallel plate chamber in the case of cobalt, but for high energy photon beams, it's only a cylindrical chamber. One would prefer a former type with 0.6 cc volume and should be waterproof. If it is not waterproof, you should have a waterproofing sleeve of PMMA or equivalent material with thickness less than or equal to 1 mm. You can see here, this is the waterproofing sleeve which is made smaller at this point and the thickness is less than or equal to 1 mm of PMMA. You need electrometer which should be calibrated, preferably calibrated with the ion chamber. Calibrated front pointer, I would prefer a mechanical front pointer. You can also use your optical front pointer if it is calibrated very accurately, or room lasers if it is nicely adjusted to the isocenter. You also need calibrated barometer and calibrated thermometer for measuring pressure and temperature. You also need a ruler for measuring the depth or a measuring scale. I would prefer a stainless steel because it has got much accurate graduation compared to a plastic one. And the worksheet, you need to have the TRS 398 worksheet for the measurement. Let us start with cobalt-60 measurement. This is the reference condition as per table 10 of TRS 398. The reference condition states that the phantom material has to be water. The chamber could be either cylindrical or parallel plate. The depth of measurement should be 5 gram per centimeter square or 5 centimeter in water, or one can use 10 centimeters also. That's permitted. The reference point of the chamber should be the central axis at the center of the cavity volume for cylindrical chambers and on the inner surface of the window at its center for parallel plate chambers. The position of the reference point of the chamber should match the Z reference, which means if you're using a cylindrical chamber, the center of the cavity volume should be at 5 centimeter or 10 centimeter Z reference. And the SSD or SED for cobalt has to be 80 or 100 depending on your machine. There are certain cobalt units which are 100 centimeter SSD. Field size has to be 10 by 10 as the reference field size. What is tissue equivalency or water equivalency for photon beam? Water is the most universal soft tissue substitute material, useful in both photon and electron beam measurements. When you say tissue equivalency, what you mean is it should match the mass energy absorption coefficient or mass stopping power or mass scattering power. The water phantom that we use for absorbed dose measurement should have a margin of 5 centimeter from the field size, nominal field size at the point of the ion chamber, and there must be 10 centimeter water beyond the ion chamber. So if you look at, this is the field size here, nominal field size. At the point of the ion chamber, it should have 5 centimeter all around, and below the chamber, you must have 10 centimeter of water. This is to provide adequate scattering condition. What comprises calibration of a cobalt-60 unit? When you say, I'm going to calibrate a cobalt-60 machine, what do you mean by that? You are going to measure the output, that is the dose rate at SSD or SAD for a reference field size of 10 by 10. And you are going to measure the shutter error or timer error. Of course, you have to make sure the timer is accurate. So output measurement and shutter error measurement or timer error measurement is necessary for calibration of a cobalt-60 machine. Let us start the measurement, filling up the worksheet. The initial part of the worksheet is more of user information, which hospital, which date you are doing, what machine you are using, Equinox 80, and what setup you are going to use. I would prefer SSD technique. Many people do SAD. The reason they have SAD, switched over to SAD is that most of our treatments, almost all treatments are SAD technique. So why not we do the calibration also in the same method. So that's why people are moving to SAD technique. But just for convenience and the fact that we have been using SSD for a long time, I would prefer SSD technique. And the reference distance in Equinox 80 is 80 centimeter. And as I said, I will measure at 5 centimeter depth in water, or 5 gram per centimeter square. The reason I will explain you when we do the actual measurement. Then you have to fill up the ionization chamber details. You have to be very careful. Here, the serial number of your ion chamber should match your calibration certificate serial number. And the NDW you get from calibration certificate. One thing you have to notice when you get the NDW, whether it is gray per coulomb or gray per nanocoulomb, you have to be very sure. Here they have given gray per coulomb, but I have converted it to gray per nanocoulomb because my electrometer reads a nanocoulomb, so it's an easy conversion factor. So I converted this gray per coulomb to gray per nanocoulomb. Other things you have to note in the calibration certificate is the reference temperature and pressure. Again, you note it is given as millibar, but I converted into kilopascals, and the temperature. And another couple of more things you have to note from here is the voltage at which the measurement was done. It is plus 300, both polarity and voltage. So that has to be noted. It is ideal to do in the same term, polarity and voltage. And coming on to the electrometer, whether the electrometer is calibrated separately, if no, don't worry, then the same factor will work. If it is calibrated separately, you will have a calibration factor. And most of the time what we do is we calibrate the electrometer and the chamber together. Sorry. The other thing you have to note is whether the range setting is the same as the calibration. So you see what is the range setting they used, and you have to use the same range setting here. Let us go on to the formalism. The absorbed dose at reference depth, Z reference, is given by dose to water for the particular energy is given by meter reading for that energy corrected for influence quantities into NDW, that is the calibration factor for reference energy, multiplied by the KQQ0, which converts this reference energy calibration factor to the energy of the user. But in this case, we are going to use cobalt 60, and most of the SSDL calibrates and provide the calibration factor with Q0 as cobalt 60. So then this calibration factor will be for cobalt 60. You don't need to have KQQ0, that will be 1. So your equation now reduces to dose to water is equal to meter reading corrected for influence quantities multiplied by the calibration factor NDW. So before you commence the measurement, you have to make sure you leave the electrometer and the chamber connected and left on for a few hours in the same room where you are going to do the measurement. The second thing is check for leakage of the electrometer. If the leakage is appreciable, you can't use it. If it is small leakage, you can correct for it. Fill the water to correct level. Check the depth of the chamber and the SSD. Please note, I said we are going to do SSD setup measurement. And let the temperature equilibrate, so leave it for about an hour. So now you have to make sure that your setup is correct. So we said we will do SSD technique. So the source to the surface distance should be kept either 80 or 100. In our case, it is 80. And I would prefer measurement at 5 centimeter. So 10 centimeters permitted, but I would prefer, I said, I measure at 5 centimeter in the case of cobalt, not for high energy. And the field size is kept at 10 by 10. Now I will start measurement. You note here, I do the measurement for 3 minutes, maybe 2 minutes. The reason I select 2 or 3 minutes instead of 1 minute is it should somehow match to the actual treatment time that you use for patients. So it's somewhere around 2 to 3 minutes. 3 minutes, so I use 3 minutes. So the meter readings are taken. I always do 3 trials and take the average. Or also, you can see that I did measurement for plus 100, which is the reduced voltage needed for recombination calculation, recombination factor calculation, and minus 300 volt, which is needed for polarity correction. So this plus 300 values and minus 300 values I will use for polarity correction. Plus 300 and plus 100 I'll use for recombination correction factor calculation, and this plus 300 will be my meter reading for absorbed dose measurement. Please note, you have to make sure SSD field size depth are correct and the chamber geometrical center at the reference point and not effective point of measurement. And note down the temperature and the pressure, apply the pressure temperature correction factor, and here the pressure temperature correction factor when you calculate for 20.5 and 101.05 is 1.003. Please note, you have to measure the temperature in the phantom and don't take the room temperature. Second is determination of polarity effect, K polarity. You remember that we did for plus 300 volts, the meter reading is 57.74, that is M plus, and we did for minus 300, the meter reading is 57.393, which is M minus. Use this equation, substitute for M plus and M minus, and your polarity correction factor is 1.002. Then you have to do the ion recombination correction factor. If you remember, we did measurement for 300 volts and reduced voltage of 100 volts. For 300 volts, M1 is 57.74. For 100 volts, M2 is 57.68. Use this equation. This equation is the equation for polarity correction for continuous radiation. Cobalt 60 being a continuous radiation, you should use this equation. Okay, so when you calculate, the polarity correction comes to about 1.0001. So the ratio of V1 by V2 should be ideally equal to or larger than 3. That means 100, 300, 100 is 3. That's fine. But sometimes you may be restricted to value of 2. For example, I have a Kapintec electrometer which has got plus 300 and plus 150. So I can do only V1 by V2 equal to 2. But now we have electrometers where you can even set 400 and 100, 300 and 100. Okay. Going back to the worksheet, now for plus 300 volts, this is the meter reading, and I said I did it for 3 minutes. So per minute, the nanocoulomb per minute is 19.27, and I noted my pressure and temperature, and we calculated the pressure temperature correction as 1.003, and the electrometer was calibrated with the ion chamber, so the factor is 1. And we also did the polarity correction, positive voltage 300 and negative voltage 300 values, and the polarity correction factor was 1.001. And we also did the recombination correction. We did for plus 300 volts and plus 100 volts, and the values were M1 were 57.74 and 57.68, and we calculated using this equation, the equation for continuous radiation at 1.0001. So when you correct your meter reading for pressure temperature, K electrode, which is 1, and polarity and recombination, you get 19.31. Now, to convert this meter reading, corrected meter reading to dose at depth, you need to multiply by NDW. You already know the NDW is 0.05373 gray per nanocoulomb. So you multiply, you get 1.0375 gray per minute. So this is the dose to water at the reference depth of 5 centimeter. Now you have to get, if you want, you have to convert the dose to water at Dmax. Some of the treatment planning systems ask you to enter at 5 centimeter depth or 10 centimeter, then you enter this. If they want you at Dmax or you want at Dmax, then divide by the percentage depth dose, which is 78 for 5 centimeter depth. This is the reason I wanted to measure at 5 centimeter. Suppose if I had measured at 10 centimeter, then the percentage depth dose would have been 56, which means I would be using a larger factor to correct to Dmax, which I don't want to do. So when I do the Dmax with 5 centimeter using a 78% depth dose value, I got 1.33 gray per minute, the dose to water at Dmax. If you had used a SAD setup, then you will be using TMR and not PDD. So you have finished output measurement, that is the dose rate at Dmax or at 5 centimeter depth in SSD technique. Now the next thing is to see whether you can measure the shutter error. Shutter error or timer error. This is the time lag for a source to reach the on position. It could affect your output measurement, and a correction should be applied to the For the timer error, correction for timer error may be sometimes very significant, and most of the cobalt units nowadays, they make such that the timer starts when the source is on position, but still there could be some timer error. So how do you determine the timer error? The method is like this. You measure for maybe 3 minutes or 5 minutes in an integrated mode, which is for a time TA, and take the value as MA. Then the same 3 minutes or 5 minutes, you divide this into 2 or 3 times. But take integrated reading. Don't do anything with your electrometer. Just allow it to accumulate the dose. Stop at 1 minute, stop at 2 minutes, stop at 3 minutes, and then start, switch on again. So your source goes off and goes on, goes off and goes on. So after maybe n is equal to 4 or something, you take the value TB by n, right? And now you have MB into TA, MA into TB. You use this equation, you can get the shatter error tau. You have to use this tau along with your time to actually get the value M1. So you have to apply this shatter error. Sometimes it could be very significant. We have finished cobalt. Now we will move on to high energy electron beam measurement. Sorry, high energy photon beam measurement. I very apologize for it. Right. Let us look at the reference condition. How is it different from cobalt? The phantom material, same, like water as we did for cobalt 60. Chamber, here you are allowed only cylindrical chamber, no parallel plate chamber is suggested for by TRS 398. And the depth of measurement is 10 gram per centimeter square or 10 centimeter depth in water. They allow 5 for low energies, maybe 4 MeV, 4 MV photons or something like that. But generally suggested even for closer to 6 MV is 10 gram per centimeter square. So the reference point again, the cylindrical chambers on the central axis at the center of the cavity volume. This point should be at Z reference of 10 centimeter, that is at the reference. So at the measurement depth Z reference, this point should be there. That means there is no effective point of measurement. SAD or SCD or SSD will be 100 centimeter and field size is 10 by 10. Please note the difference, no parallel plate chamber allowed, and depth has to be 10 centimeter in water for high energies. Let us come to beam quality. Why do you need to know beam quality? I know it is 6 MV, the energy is 6 MV. No, that's not right. That is what we call nominal energy. The reason is 6 MV of true beam will not produce the same depth dose as 6 MV of synergy electron machine. So unless you have two machines very nearly identical and done the beam matching, the percentage depth dose, even though the nominal energy is same, will be different. So you need to have a method to identify the beam quality. Both are 6 MV, but the beam quality could be slightly different. So TRS 398 provides tissue phantom ratio TPR 2010 as the beam quality index, energy index. APM tells you to use PDD at 10 centimeter depth, but TRS 398 recommends TPR 2010. So what is TPR 2010? You know tissue phantom ratio. Tissue phantom ratio is the ratio of dose to a depth 20 centimeter to at 10 centimeter without moving the chamber position, without altering the chamber position. So the distance from the source to the chamber is now 100 centimeters, right? SAD is 100 centimeter. You measure, now you are at a depth of 10 centimeter, you get D10. You got the D10. Now what you do is you don't touch the chamber, but increase the level of water by another 10 centimeter. So now the depth becomes 20 centimeter, your SSD becomes 80 centimeter, but SAD remains as 100 centimeter. That is the position, distance between source to the chamber is maintained the same 100 centimeter. But the chamber is at 20 centimeter depth. Now you measure the dose at 20 centimeter. So your TPR 2010 is dose at 20 divided by dose at 10. This value is the energy index. So why TPR 2010 as energy index? It is independent of electron contamination in the incident beam. It is also a measure of effective attenuation coefficient. Since TPR 2010 is ratio of doses, it does not require the use of displacement correction factor for cylindrical chambers. TPR 2010 is in most clinical setups not affected by small systemic errors in positioning the chamber. Okay, so the next is, now you know the energy index. What is next? You need to know what is the KQ, because you are not using cobalt, you are using a energy which is different from the energy that was used for calibrating your ion chamber, NDW. So your NDW is for cobalt. Now you want to convert that from cobalt to the energy that you are using. So you need to have the KQQ0. So how do you get the KQQ0? Ideally, you should do a measurement like this, calculation like this, NDWQ by NDW cobalt, but you don't have the NDWQ. If you had that, then you don't have this problem. So what one can do now is TRS 398 luckily provides you all the values of KQ for various beam quality for various ion chambers. So you go to the table 14, go and look at what is your TPR 2010. My TPR 2010, for example, is 0.68, and I'm using former capping tech. Then my KQQ0 is 0.992. Suppose I'm using 10 MB and it is 0.74 or somewhere between 0.72 and 74, then I will have to interpolate here and take it as 0.986. So now I have got my KQQ0, right? I will start measurements like earlier we did for cobalt. I will use 200 MU because that is closer to my MUs that I use for treatment. And 3 trials done and the mean value is taken for plus 300, which is my meter reading for observed dose measurement. I also do for minus 300 so that I can do the polarity correction. And I also do for plus 100, that is the reduced voltage, so that I can do the recombination correction factor. So I have got all these values. So next thing is, as you know, that the ion chamber is kept here, where it is waterproof sleeve has less than 1 mm of PMMA. So please make sure your depth, SSD, field size are correctly measured. And more importantly, the depth is at the geometrical center of the chamber and not at the effective point of measurement. Why? It could be a very good question. Because the effective point of measurement correction is already incorporated in KQQ0, you don't need to do that. You can take the geometrical center here. Then go back to the worksheet, start filling it up, the user details, date. I'm doing for TrueBeam STX at 6 MV and my nominal dose rate is 600. My beam quality TPR 2010 I measured is 0.663. And I said I will do for SSD technique, and my reference depth is 10 gram per centimeter square or 10 centimeter depth. And my reference distance is 100 centimeters. Next, fill up the ion chamber details. Be careful, you use the same ion chamber for which the calibration factor is available, with calibrated in an SSDL, and the calibration certificate provides you these details. And it is calibrated for cobalt. The TPR 2010 is 0.663. Please note what was the reference temperature and pressure for the calibration certificate, and also the voltage they used, polarizing voltage, and the polarity. And you need to mention what electrometer was used, and the electrometer was calibrated separately or with ion chamber. We always calibrate with ion chamber, so don't worry about it. And also note the range setting in your electrometer. You have to use the same range setting. So you measure the pressure and temperature, and pressure temperature correction has to be applied. The pressure temperature correction, the same formula, P0 by P into T0, T by T0. Of course, you have to convert that here by adding 273.2. So in our case, it is 26 degrees centigrade and 99.1 kilopascal. So when you apply this, you get a pressure temperature correction factor of 1.045. Please note the temperature has to be measured inside the water phantom. Next is the polarity effect, K polarity. So you remember that we did 2 measurements. One is for plus 300, one is for minus 300. The plus 300, you got M plus, which is 24.16, minus 300, you got M minus, which is 24.14. Use these two values, substitute here in this, and get K polarity, which is 0.9995. The next is ion recombination factor. If you remember, we did measurement for plus 300, also reduced voltage of plus 100. Now, this is a pulsed beam. So you cannot use the same equation like cobalt. You have to use the pulsed beam equation and substitute the values of M1 for plus 300, M2 for plus 100, here as M1, M2. But A0, A1, A2 will have to be obtained from the table 9 in TRS 398. These are constants and they are provided. Now, the A1, A0, A2 are for the V1 by V2. You have to note, in our case, V1 by V2 is 3, so you have to take it from here. And the Ks, the recombination factor, is 1.004. Again, note the V1 by V2 should be ideally equal to or greater than 3. Going back to worksheet, you mentioned the value you got for plus 300. So much nanocoulomb per 200 monitor units. Then per monitor unit divide by 200, you get 0.1208. And note down your room temperature and pressure. Apply the PTP correction we calculated at 1.045 pressure temperature correction. And your electrometer correction is 1. And we also calculated the polarity correction factor as 0.99952. And the recombination corrector factor we calculated as 1.04. You remember all this, we used the equation for pulsed beam. Apply these values of 1.004 and 0.99952 and 1.045 pressure temperature correction on the meter reading, you get a corrected meter reading of 0.127 nanocoulomb per mu. So you got the corrected meter reading at the depth of 10 centimeter, but you have to convert this meter reading into dose to water at the depth. How do you convert that? You multiply by the NDW factor. That is your calibration factor. But the calibration factor was for cobalt, so you also need KQQ0, which we found out from the table for KQQ0, which is 0.9904. So now we get the dose at depth 10 centimeter reference depth to water is 0.6738. Some treatment planning system will ask you to feed this value. Sometimes they ask what is the dose at Dmax, then you have to divide by the percentage depth dose. For 6 MV, the percentage depth dose in our TrueBeam is 66.4, right? So when you divide, you get 1.009 or 1.01. But if you want to tune it to 1, you are welcome to tune this. If you are used SAD setup, then you won't be using the percentage depth dose, rather you will be using the tissue maximum ratio to calculate. So this is how you do the absorbed dose measurement for high energy photon beams. And we will go on to the next one, which is for high energy electron beams. But before this, before we go on to that, I would request you to complete the assignments against this lecture. I hope you enjoyed the lecture. And I hope it was very useful. Thank you very much for your listening.